Now example 1.11. The electric field components in figure 1.27 are Ex equal to alpha x raised to 1 by 2, Ey equal to Ez equal to 0, in which alpha equal to 800 Newton per Coulomb meter raised to 1 by 2. Calculate A, the flux through the cube, and B, the charge within the cube. Assume that A equal to 0.1 meter. Now see the given situation, that is as shown in the figure. X component of electric field, that is alpha x raised to 1 by 2. It implies that electric field that is in x direction, because y and z components are given to you 0. Value of alpha 800 Newton per Coulomb meter raised to 1 by 2, and A, that is the side of the cube, 0.1 meter. Okay. Now here we can easily understand this thing. Flux will be associated with the surfaces which are perpendicular to electric field. The surfaces which are parallel to electric field, flux will not be associated with those surfaces. Now electric field that is in x direction means we have to think about the surfaces which are perpendicular to x-axis. So first we think about this particular left hand side surface, okay, this one, which is perpendicular to x-axis. Okay, now flux associated with that particular surface. So electric field at the position of left surface dot delta SL. Now electric field that is alpha a raised to 1 by 2, it is in x direction, so I caret. Now area vector for this particular surface, area vector is always represented in outward direction for the closed surface. So here delta S, that is in negative x direction, side that is A, so we can write the area is A square. So in vector form we can write minus A square I caret. So resultantly we will get flux associated with left surface, that is minus alpha a raised to 5 by 2. Then flux associated with right surface 5r, that is ER dot delta SR. Now electric field at the position of this right surface. So this right surface that is at distance 2a from the origin. Clear? So here we have to take x, that is equal to 2a. For left, see, left was at a, so we considered x equal to a. But now here for right we have to take x equal to 2a. So alpha into 2a raised to 1 by 2 I caret dot. Now here area vector of this one, that is also in positive x direction. So we can write a square I caret. Resultantly we will get flux associated with right surface, that is alpha into 2 raised to 1 by 2 into a raised to 5 by 2. So net flux passing through this particular cube, that is 5r plus 5l, that is root 2 alpha a raised to 5 minus alpha a raised to 5. So resultantly we will get 5, that is, take alpha a raised to 5 by 2 common. So into bracket root 2 minus 1. Alpha, that is 800, a, that is 0.5 raised to 5 by 2 into root 2 minus 1. Now solve this one, you will get total flux phi passing through this particular cube. Now charge enclosed by the surface that we want to calculate. So as per Gauss's theorem, flux associated with any closed surface, that is the ratio of the net charge enclosed by the surface to epsilon 0. So phi, that is q upon epsilon 0. So q, that is phi into epsilon 0. Substitute the value of phi which we calculated here to this one, and epsilon 0, that is 8.85 into 10 raised to minus 12. Solve this one. So we will get the net charge enclosed by this particular surface. Clear to all of you? Next, example number 1.12. An electric field is uniform and in the positive x direction for positive x and uniform with the same magnitude but in the negative x direction for negative x. It is given that E equal to 200 I caret Newton per Coulomb for x greater than 0 and E equal to minus 200 I caret Newton per Coulomb for x less than 0. A right circular cylinder of length 20 centimeter and radius 5 centimeter has its center at the origin and its axis along the x-axis so that one phase is at x equal to plus 10 centimeter and the other is at x equal to minus 10 centimeter as shown in the figure. Now question A. What is the net outward flux through each flat face? B. What is the flux through the side of the cylinder? C. What is the net outward flux through the cylinder? D. What is the net charge inside the cylinder? Now see, this one is the cylinder whose axis is coinciding with x-axis and center of the cylinder is coinciding with origin of the Cartesian coordinate system. Now, in positive x direction, electric field that is 200 I caret Newton per Coulomb. In negative x direction, it is minus 200 I caret Newton per Coulomb. So first solve question A. Flux, net outward flux through each flat face. Now see, if we think about the left flat face, this one, then flux passing through it, that is E1 dot A1. Now area vector, that is also in negative direction. Now E1, that is minus 200 I caret dot. For this particular flat surface, the area, that is pi r square, and it is in negative direction, so minus I caret. So 200, 3.14 r, that is 5 centimeter given to you. So that is 5 into 10 raised to minus 2 whole square. Solve this one, you will get the flux passing through left side flat face. Then flux passing through right side flat face. So E2 dot A2. Now E2, that is 200 I caret, A2, that is in positive x direction. So pi r square I caret, then 200, 3.14, radius 5 into 10 raised to minus 2 whole square, I caret dot I caret, that is 1. Solve this one, you will get the answer. Then after B, question B. What is the flux through the side of the cylinder? Now, if you want to calculate the flux passing through the side of the cylinder, then consider here infinitesimal small surface element at any point on that particular cylindrical surface. Suppose as shown in the figure, that is delta S. Now here, this area vector for this surface element, that is perpendicular to the electric field vector. Either you take this one on right hand side, or if you take it on left hand side, means on negative x side. In both the cases, delta S is perpendicular to the electric field vector. Therefore, E dot delta S, that is 0. So flux associated with cylindrical surface, that is equal to 0, right? Then after, net outward flux through the cylinder. So we can write flux phi, that is equal to flux passing through left flat face, flux passing through right flat face, plus flux passing through cylindrical surface. So for left and right flat faces, the flux that is same one, so we can write 2, and whatever is the answer here calculated for left or right, substitute it, and then flux passing through cylindrical surface, that is 0. Now we will get the net outward flux through the cylinder. Then after, net charge inside the cylinder, so as per Gauss's theorem, we can write Q, that is epsilon 0 into phi. Net flux we calculated here. So now we have to substitute this value of flux 5 and then value of epsilon 0, we will get net charge inside the cylinder. Clear to all of you? Now, applications of Gauss's law. First, let's calculate the field due to infinitely long, straight, uniformly charged wire. Now see here, if we consider any point P, which one is situated at perpendicular distance R from the wire, this one, okay. Now if we turn the wire, then this particular point P will be rotated and will form a circle having radius equal to R. But we can understand this thing, each and every point on the circumference of this particular circle having radius R, that is with the same symmetry as P, and electric field at each and every point that will be radially outward. If here this particular wire is positively charged and if it is negatively charged, then radially but towards the wire. See here how it will be radially. If we consider any two infinitesimal small wire elements which are at the same distance from this particular center, we can say, then at point P, if we think about the electric field due to both the elements, then electric fields will be in the directions as shown in this figure. But now if we take the components of this electric field, vertical and horizontal, then vertical components here parallel to this particular surface will cancel the effect of each other, and horizontal will be sum up in this direction. So resultant field, that will be radial one. Here suppose the linear charge density of the wire, that is lambda, means charge per unit length of the wire. Now here if we consider the Gaussian surface, which one is a cylindrical one as shown in the figure, having radius equal to R and length equal to L. Then by applying the Gauss's theorem to this particular cylindrical Gaussian surface, one can easily calculate the electric field. Now, flux associated with this cross-sectional surface is this upper one and this lower one. That will be 0 because their area vectors for upper one vertically upward, for downward vertically downward, but both the area vectors will be perpendicular to this radial electric field. Therefore, flux associated with this cross-sectional upper and lower surface will be 0. Now, flux passing through the cylindrical surface that we have to calculate. Suppose here we consider infinitesimal small surface element delta S on the cylindrical surface. Then its area vector that will be radially outward, electric field that is also here radially outward because our lambda that is greater than 0. So phi that is equal to E dot delta S for this particular element, and if we want to calculate the total flux, then we have to take the summation of it. So sigma E dot delta S will give you the resultant flux. Now E is same one at each and every point on that cylindrical curved surface, because each and every point on the cylindrical curved surface that is at the same perpendicular distance r from the infinitely long wire. So E sigma delta S cos theta, theta that is 0. So here we can write cos 0. So E sigma delta S, that is the summation of the area of each and every element of this particular cylindrical surface, which will give you total cylindrical surface area, and that is 2 pi r L. So we can write now flux phi, that is E into 2 pi r L. This one is calculated as per the definition of flux. But as per Gauss's law, flux passing through any closed surface, that is net charge enclosed by that surface upon epsilon 0. Okay, so here we can write now this particular charge enclosed by the surface, that is how much. So here charge per unit length of the wire is lambda, then charge on the length L, because here length of the cylinder under consideration, that is L. So charge enclosed by the cylinder, that is charge residing on L length of the wire. So we can write now charge per unit length is lambda, therefore charge on length L is how much? So Q, that is lambda into L. So we can write now E into 2 pi RL equal to lambda into L upon epsilon 0. L is cancelled. So E, that is lambda upon 2 pi epsilon 0 R. And in vector form we can write E, that is equal to lambda upon 2 pi epsilon 0 R into R caret, where R caret is the unit vector in the direction of electric field. Clear to all of you? Now second application. Field due to uniformly charged infinite plane sheet. Suppose as shown in this figure, we have uniformly charged infinite plane sheet having surface charge density, that is sigma. Surface charge density means charge per unit area. Now to calculate the electric field at any point on either side of this particular surface. Here, let's consider the rectangular parallelopiped Gaussian surface. Here, on right hand side and on left hand side of this particular charged infinite plane sheet, if we consider 2 points which are situated at the same distance from the sheet, then from the symmetry we can understand this thing, the field intensity will be same one at both the points. Now, if we consider this cross-sectional surface on right hand side and this particular cross-sectional surface on left hand side, suppose its area is A. So electric field of this particular charged sheet will be perpendicular to these cross-sectional surfaces, but it will be parallel to the sides of this parallelopipe, and therefore flux passing through these sides of the parallelopipe Gaussian surface, that will be equal to 0. Now, if we calculate the flux passing through these left hand side and right hand side cross-sectional surfaces, then we can write 5L, that is equal to E dash dot A dash, but magnitude of electric field, that is suppose E, area, that is A. So we can write E A cos theta, but here area vector and field both are in the same direction, so theta is taken 0. So E into A. Similarly, the flux passing through this right side cross-sectional surface phi r, that is E dot A. So we can write that is also E A cos 0, that is E A. It implies that here the total flux associated with this rectangular parallelopiped Gaussian surface, that is phi equal to flux associated with this left cross-sectional face EA. For this right side cross-sectional face EA, and for the sides of this parallelopipe rectangular Gaussian surface, that is 0. So simply we can write phi, that is EA plus EA, that is 2EA. And as per Gauss's theorem, that is equal to Q upon epsilon 0, where Q, that is net charge enclosed by this Gaussian surface. So here charge per unit area is sigma. So charge on area A, that is how much? So that is sigma into A. So we can write 2EA, that is equal to, now Q is replaced by sigma into A upon epsilon 0, A cancelled. So electric field, that is sigma upon 2 epsilon 0, and here you can observe this thing. At any point the electric field is constant. In vector form we can write electric field, that is sigma upon 2 epsilon 0 n caret, where n caret is the unit vector in the direction of electric field. Clear to all of you? Now, field due to uniformly charged thin spherical cell. Suppose here we have uniformly charged thin spherical cell with surface charge density sigma, having radius equal to capital R. And suppose total amount of charge residing on the spherical cell, that is Q. Here we have to calculate the electric field outside the spherical shell as well as inside the spherical shell. Suppose first we consider any point outside the spherical shell. So here consider the Gaussian surface. Which one is a spherical one passing through that point where we want to find the electric field. So see, as shown in this figure, the Gaussian surface under consideration, that is this one with radius equal to small r, where small r is greater than r. It implies that now we are considering the point which is outside the charged spherical shell. And the point where we want to find the electric field, that is on the spherical Gaussian surface. The center of the spherical Gaussian surface is coinciding with the center of spherical shell. Now, flux passing through this particular spherical Gaussian surface, that is, as per definition, we can write sigma E dot delta S. Delta S, that is infinitesimal small element on the Gaussian surface, and electric field at the position of this element, that is E, but electric field that is radially outward. Here sigma is greater than 0. So electric field and this area vector both are radially outward, so are in the same direction. So theta equal to 0. So cos theta, that is cos 0, that is 1. So we can write the sigma E dot delta S, that is E sigma delta S. E, that will be same one, because each and every point on this particular Gaussian surface, that is at the same distance, small r, from the center. So due to this spherical symmetry, the field will be same one at each and every point. So we can write now flux passing through this Gaussian surface, that is E sigma delta S. But as per Gauss's theorem, that is Q upon epsilon 0. So we can write E sigma delta S, that is Q upon epsilon 0. So E sigma delta S, that will give you the total spherical surface area of the Gaussian surface, that is 4 pi r square. That is equal to Q upon epsilon 0. So we can write E, that is equal to Q upon 4 pi epsilon 0 r square. Or in vector form, we can write E, that is Q upon 4 pi epsilon 0 r square into r caret. Now see this equation. This one is equation exactly like the electric field due to a point charge Q at a point which one is situated at distance r from the charge. So here we can understand this thing. This entire spherical charge distribution behave like a point charge concentrated at the center of the spherical shell for any point which one is outside the shell. Clear to all of you? Now Q, that is the total charge residing on this particular spherical shell. So if you want to write the answer in terms of surface charge density, then total charge, that is charge per unit area into total area. So sigma into 4 pi capital R square, that is your Q, upon 4 pi epsilon 0 small r square as it is. So 4 pi cancel. So electric field, that is sigma r square upon epsilon 0 small r square. So you can write the equation of the electric field in terms of charge residing on the cell like this, and then electric field in terms of surface charge density of the spherical shell as this one. Clear to all of you? Now think about the electric field at any point inside the spherical shell. So here again consider the spherical Gaussian surface having radius equal to r dash, for which the center of the Gaussian surface is coinciding with the center of spherical shell. And r dash is less than capital R. It implies that this spherical Gaussian surface is inside the charged cell. And now we want to find the field at any point on the surface of this Gaussian surface, each and every point that is at the same distance r dash from the center. So we can write flux phi, that is sigma E dot delta S, that is equal to, as per Gauss's theorem, Q upon epsilon 0. But see here, Q, that is the charge enclosed by Gaussian surface. Here entire charge is outside the Gaussian surface. So net charge enclosed by the surface is 0. So here we have to take Q equal to 0, this one. So if we take Q equal to 0, then E equal to 0. It implies that inside the charged spherical shell at any point, the electric field is 0. Clear to all of you? Now example 1.13. Say, an early model for an atom considered it to have a positively charged point nucleus of charge Ze, surrounded by a uniform density of negative charge up to a radius capital R. The atom as a whole is neutral. For this model, what is the electric field at a distance R from the nucleus? Now see here. In this given atomic model, the total amount of positive charge, that is Ze, which one is at the center? Then total amount of negative charge, that is minus Ze, because it is given to you. This atom is as a whole electrically neutral. And this negative charge is uniformly distributed over this radius R. It implies that here we can write this total charge, that is total volume into volume charge density. Volume charge density of negative charge, that is the charge per unit volume. So charge per unit volume is rho, therefore charge in volume 4 by 3 pi r cube is how much? So you will get that minus Ze equal to 4 by 3 pi r cube rho. Now let's consider first the field at any point inside the atom. It implies that consider the point which one is situated at distance small r from the center of the atom, where small r is less than capital R. Now consider the Gaussian surface, that is a spherical one with radius equal to small r. Now flux passing through that particular spherical Gaussian surface, that is sigma E dot delta S equal to Q upon epsilon 0. Now electric field E will be same one at each and every point on the Gaussian surface as per spherical symmetry. So E into sigma delta S, that is 4 pi r square, equal to Q upon epsilon 0. But Q, that is the charge enclosed by this Gaussian surface. It is how much? That we have to calculate first separately. Now net charge enclosed by the Gaussian surface. So see, this entire positive charge is inside the surface, but inside the surface negative charge, that is only we have to consider which is inside this one. So Q, that is positive charge Ze plus negative charge, that is 4 by 3 pi r cube rho. Now here rho, that is minus Ze upon 4 by 3 pi r cube. So this Ze as it is, 4 by 3 pi r cube as it is, and now your rho, that is replaced by minus Ze upon 4 by 3 pi r cube. So resultantly we will get this 4 by 3 pi cancelled, and we'll get Q, that is equal to, take Ze common, so 1 minus small r cube upon capital R cube. Substitute this value of Q in this equation. So E into 4 pi r square equal to 1 upon epsilon 0 into Ze into 1 minus small r cube upon capital R cube. Therefore E equal to, take this 4 pi r square on right hand side, so Ze upon 4 pi epsilon 0 r square into 1 minus r cube upon r cube. Therefore E equal to Ze upon 4 pi epsilon 0, take this r square inside the bracket, so 1 upon r square minus small r upon capital R cube. This is the electric field at any point inside the atom which one is situated at distance small r from the center of the atom. Now consider the point which is outside the atom. So field at any point outside the atom. So again, for that we can consider the Gaussian surface, which is spherical one having radius equal to r dash. But here when r dash is greater than r, entire charge of the atom, that is enclosed by this particular Gaussian surface. So atom as a whole is electrically neutral. Okay. So net charge enclosed by this particular Gaussian surface is 0. So when Q equal to 0, the net electric field, that will be also 0. It implies that outside the atom at any point, the electric field, that is 0. Clear to all of you?